This is a second video on the temperature control lab. In this case, we're going to model convective heat transfer from the device. It's going to heat up, the temperature is going to rise, and then as a result, you're going to have some natural convection that is going to carry the heat away. We want to model that with an energy balance and then compare it to the measured values from the temperature control lab. So let's go ahead and get started with this. If you'd like to follow along with the source code, there is a link right here to the source. Just go ahead and select that and it'll bring you to the web page with all of the source code and other things that we're going to be covering here. Okay, so let's get started. We have we want to simulate an energy balance model with convective heat transfer only. Okay, so here's our heater. You can see one of those right here. This is temperature 2. The one that we're going to be dealing with is right here. You can see a little temperature 1, and there's also a Q1 or a Q2 on the other side that you can see. Okay, so if we're doing an energy balance, we're going to start with conservation of energy, and that's going to be for an incompressible, we don't have fluids, and so we're just going to have H in minus H out plus, the heat that is generated from the heater. In this case, we're just going to have a couple terms as this one right here, we have our enthalpy, and that is going to convert to mass times heat capacity times the temperature, and the mass and the heat capacity are going to be assumed to be constant. And then we also have our convective heat transfer here with an overall heat transfer or overall heat transfer coefficient, and then times the area times temperature of the ambient minus the temperature. And then we have on this side, on the right side, we have that is our an alpha value, which relates the heater percent. So the heater can go anywhere between 0 to 100, and we can adjust that up or down. Okay, and that term right here, the alpha, is 0.01, and that is going to be equal to watts per percent heater. So it converts the percent of the heater into a watts that are dissipated. So if you're at 100% heater, you're dissipated about 1 watt. Okay, so let's start with some of these other values as well. We just have the mass, the area, surface area, the heat capacity, okay, and also an ambient temperature. You can change that ambient temperature if you'd like. And we want to show a step for 5 minutes when the heater is adjusted to 50%. So we're going to get started with this code. Here's a temperature control lab step response. I'm just going to, like I did in the last video, I'm just going to run through this one a little bit more quickly in this case. Import numpy, matplotlib, and get your temperature control lab module as well. Just pip install TCLab. Import time. We're going to go for 5 minutes, 300 seconds. Here's the lin space that equally spaces values between 0 and 300 with 301 time points. We're going to get some data by connecting to the temperature control lab device, and then create an array or a list of 1. Set our heater to 50, and then we'll loop through. This is going to be 300 times. We'll sleep for 1 second. We'll print the current temperature, and then append a current temperature to that list, which is T1. And then we'll close the lab, and then we'll plot it. Okay, so we're just going to plot T1, add some Y label and X label and a legend, and then show it. So that'll go for 5 minutes, but it doesn't have our simulation model in there. And so for that, we can either use ODE or Gecko. I'll show ODE first. We need to import from SciPy integrate. We're going to import ODE. Next, we're going to create the simulation. Here, we're going to define this is going to be our equation. Okay, I'm going to put in some of the constants, the overall heat transfer coefficient, the area in meters squared, Cp, CCP is 500 watts per meter squared Kelvin, or watts per kilogram Kelvin. And then there's our mass in kilograms, there's our alpha value, and our ambient temperature. And now this is our equation. Now when you're simulating an ODE with ODE int, you have to put everything on the right hand side. The only thing that's on the left hand side that you're evaluating is the derivative. So the derivative of the temperature. So we have our convective heat transfer, we have our heat generation or dissipation from the heater, and then we have to divide by the mass times the heat capacity on that side. Okay, we're going to return CADT. Okay, we're going to add, we want to get a TSIM added to our plot. And so we're going to just integrate with ODEint this function that you see right up here. And we're going to start with 23, which is our ambient temperature. And then our time, and we had defined that right up here in terms of the 301 values between 0 and 300. Okay, and then when we run this, it's going to generate this. Okay, so I'm going to go ahead and just run this one now. I have my convective ODEint, and let's just go ahead and run this, and I'll explain the gecko one, and then we'll hopefully see the results in just a little bit. Okay, so it's going to first of all connect to the temperature control lab device. Okay, and there you can see the version, and it's connected, and you can see the temperatures that start to print every second, and the heater's turned on to 50%, so you can see the temperatures start to rise. And okay, so here it goes. I'm just printing one line at a time, one temperature at a time, as it's collecting it from the Arduino. Alright, let's go back to the gecko method for solving differential equations, and if you'd like a little bit more of a tutorial on this as well, there is an introduction here on solving with ODEint. Alright, if I select that, you can see a little bit more of a tutorial on setting up and solving differential equations with the ODEint, the SciPy integrate package. And then if you want to, there's also the same tutorial but with gecko. This is another package for solving differential equations, and you just pip install gecko, and a little bit more instruction about how to set up and solve problems with gecko, those same examples. Okay, but let's go back to this one that we had with the convective one. We're going to, first of all, if you don't have gecko, pip install it, and then from gecko import gecko, and then we're going to create our simulation. We're going to create a new model, and we're going to call that M. Now we do want to be careful because M is also our mass in our model, so we don't want to create a variable that's also M. There's our overall heat transfer coefficient, the area, and the CCP, the heat capacity. The mass, so I'll call it mass instead of M, and then alpha, and then TA. That's our ambient temperature. We'll create a new variable and give it an initial condition of 23. There's our equation. We're going to have mass times heat capacity times TC. Now in this case it's our derivative, so we're going to put dot dt with open and closed parentheses. Don't forget to use the double equal sign there. Okay, and then U times A times the difference between the ambient and the temperature of the heater plus alpha times 50. Okay, so that could be, you could write another Q parameter if you wanted, or you could just add A equal to 50. We're going to switch this to I mode 4, which is dynamic simulation, and then we will solve it, and then we will add it to our plot. Right down here on line 32, here's where we add that simulated value to our plot. Okay, so that should give us the exact same results as the convective ODEint, and let's just see how that one is doing. And I may pause it for a little bit and then come back when this thing is finished, and we can look at some of the results. Okay, and Actually, I think I had a result from before. Let me go back down here. Okay, here it is. Here's one of the other results that I had from running it earlier. You can see the simulated and measured values. So you can see that the heater turns on right here and to 50%. Let me go to 50. Alright, and you can see there's a little bit of a delay here that we're not quite capturing. And we'll talk about that a little bit more about some of the other models that we could use. It looks more like a second order model versus a first order model. The blue line is our simulation, and you can see that it's predicting a little bit high over what the measured value is. And so there's obviously a little bit of difference there, and we'll try to do some things later with regression or other things to adjust the parameters so that we fit better to the data. But this is just a pure simulation based on some guess values for some of those, overall heat transfer coefficient and the alpha. But we'll work on getting better values for those later. Okay, so I'll go ahead and just pause this, and then we'll look at it again in just a second once it's done. Okay, so it just finished, and you can see that the room that I'm in right now is a little bit cooler than it was from before, so the data is shifted down just a little bit. Okay, started at about 17 or 18 Celsius versus this one was in a room where it was 25 Celsius, so you can see that it matched just a little bit better. I had assumed an ambient temperature of 23, or I probably should have put 17 in here, shifted this blue line down. But you can see a fairly good approximation with without this offset. This is a very basic lumped parameter model. We're going to, in the next exercise, we're going to add radiative heat transfer as well, and try to quantify how much is being lost through convection, the natural convection, versus radiative heat loss.